SimHash answers may be similar. MinHash lets you control similarity and scale. This is the workflow you'll know how to run when we're done, which indexes texts and removes near duplicates using a chosen similarity threshold. I'm Professor Pi, teaching search and IR with simple Python. Near duplicate content is a real pain. You host many documents, and users see the same text in multiple places. You want one canonical copy and fast lookups. MinHash with LSH helps by spotting documents that share most of their words without comparing every pair. It trades exactness for big speedups, so you can dedupe thousands or millions of short texts in a practical time. Intuitively, MinHash turns a set of word pieces into a small fingerprint. Two documents with similar sets get similar fingerprints. Locality-sensitive hashing, or LSH, then buckets those fingerprints, so we only compare promising pairs. Strengths are speed and tunable recall. Weaknesses are approximation and parameter sensitivity. We will build a small pipeline that first creates word pair shingles, then sketches sets into MinHash signatures, and bans those signatures for candidate bucketing, then filters by an estimated similarity, and finally drops duplicates to produce a compact corpus. No deep math, just a clear path you can scale later. Now we'll extract simple singles and compute a baseline overlap. This snippet extracts word bigram shingles for each document and measures how similar two documents are using Jaccard. The variable k sets the shingle size, and the list docs holds a few short texts to compare. The function toke lowercases and tokenizes each document into words, and the function sh builds a set of adjacent word pairs. The list s stores each document's shingle set, and the final print computes the Jaccard overlap between the first two sets. Increasing k makes matches stricter, while smaller k is more forgiving. The printed Jaccard 01 shows a baseline overlap to later approximate efficiently. Next, we'll sketch sets into compact signatures with MinHash. This example creates compact MinHash signatures so we can approximate Jaccard without enumerating all shingles. The list U gathers all unique shingles, and RID assigns each a stable integer ID. The list AB holds 40 hash function coefficients, and the function H maps a shingle ID through each hash. For each document set S, the signature sig stores the minimum hashed value per hash function, capturing a sketch of the set. The final print reports the fraction of matching signature positions for documents 0 and 1. More hash functions improve accuracy, but increase memory and time. The printed MinHash 01 mirrors the baseline Jaccard closely. Then, we'll group signatures into bands to find collisions cheaply. This snippet partitions each MinHash signature into bands and groups documents that match within any band. The variables b and r set the number of bands and rows per band, respectively. So each key is a band index and a small tuple slice from the signature. The dictionary b collects document indices for each bucket, using setDefault to append matches. The variable n sums pairwise combinations from buckets to count candidate comparisons. Lower r or higher b creates more buckets and increases recall, but may add false positives. The reverse tightens matching. The printed candidates shows how many pairs will be checked further. After that, we'll turn buckets into candidate pairs and filter them. This snippet turns LSH bucket collisions into unique candidate pairs and then filters them by an adjustable similarity threshold. The variable t controls how strict we are, and the function sim measures the fraction of matching MinHash positions between two documents. The set P gathers all unique unordered pairs extracted from buckets with more than one member. The list keep retains only candidate pairs whose estimated similarity meets or exceeds T. Increasing T reduces false merges, but risks missing near duplicates. Decreasing T is safer, but may require more downstream checks. The printed kept pairs shows which documents are likely near duplicates. Finally, we'll pick which documents to keep and produce a deduped corpus. This example produces a simple, deterministic dedupe set by keeping the first document in each near duplicate pair. The set drop collects all second elements from the kept pairs, which we elect to remove for a baseline policy. The list kept gathers the remaining indices from the original docs, and unique materializes the filtered corpus. You could swap policies to prefer longer content, lower latency renderings, or a relevance score when available. The printed kept IDs confirms which documents survive, giving you a small, scalable baseline for near duplicate removal with tunable similarity. In a real pipeline, you would map document IDs to storage keys and run the same steps as a batch job or a periodic stream. Replace the simple keep policy with business rules or a relevance model to choose which duplicate to preserve. The same MinHash signatures can feed a search index for fast, similar item queries. Recap: MinHash with LSH makes set similarity cheap by sketching and bucketing. Use it when you need to dedupe large text collections or find near duplicates quickly. Caveat: it is approximate and sensitive to the number of hash functions, bands, and the similarity threshold. Next step: tune the number of hash functions, the banding parameters, and the similarity threshold while measuring recall and false positive rate on a labeled sample. If short, practical IR helps, subscribe and watch the IR videos.